Recordings rolling. It's Thursday, March 27th. So we're continuing the review with rotational dynamics. So by AP they split this into units 5 and 6. I think unit 5 is like rotational inertia and torque, and then unit 6 they get more to angular momentum and rotational kinetic energy. We're just gonna put this all together. Oh, there's also rotational kinematic motion, which we did touch on back before spring break. So we'll look at this a little bit again today because it's part of all this, and it's worth brushing up on again anyway. Maybe we'll do this a little faster. All right. So you guys get so far with what we're doing. You guys got your notes out. There's of course always paper on those spills in the room if you need paper. All right. So let's look at all the variables and units that could be associated with any of this rotational kinematics here, rotational dynamics down here. We got a little centrifugal acceleration, centrifugal force here, which we're not focused on today, but that should look good, right? So, guys, what is this letter right here? Theta, Greek letter theta. And what do you use to what does that represent as a variable? Yeah, angular displacement or an angle, right? And there's at least 3 units you can use. Guys, what's one unit you can measure this in? Degrees. And you said what else? Radians. Yeah, and you can also measure maybe some number of revolutions. So you'll hear all 3 of those. But which one is like the most mathematically pure way to describe an angle out of this? Yeah, radians. Yeah, and that's what I put here, radians. Okay. So that when you get to that turntable physics, which is going to show up, right here you go. Okay. If you want to connect, say how far is something moved in a linear sense, how far is this turntable turn? Okay. How far it's turned, you have to quantify in radians to apply this formula. Okay. Same thing with those kinematic formulas. Okay. Guys, what is this letter? Omega, and that stands for what? Angular velocity. So how fast is the turntable turning? You could say the Earth rotates at 1 revolution every 24 hours. That would be some kind of omega, wouldn't it? A fast rotating. Okay. And what's the main unit for that? How do you quantify that? Radians per second. Okay. How about if you see alpha, angular acceleration, and that's quantified in radians per second squared. There you go. So if you have a turntable that's speeding up or slowing down its rotation. Okay. All right, so I'm going to skip over these yellow rows. You guys know those from. All right. So here's some stuff we haven't looked at in a couple of months. Guys, what does capital I stand for? Yeah, rotational inertia. Okay. And okay, that ends up having these units here, kilogram meter squared, which, well, here. So some kind of mass times distance squared, isn't it? Okay. Actually, that's the formula for a point mass relative to some axis of rotation. Right? Some mass times distance squared. Okay. You guys see those? There's a couple meter sticks over there leaning against the wall by that fire blanket. Okay. It's got some masses taped onto it and tied on with strings, okay, but in different locations. So you have to remember passing this around and shake it back and forth. They have different rotational inertia. It's not just how much mass; it's how is that mass distributed. Okay. How about what's this letter right here? Yeah. So Greek letter tau, which stands for torque. Yeah, tau is torque. Okay. And guys, what's a good unit? How would you measure torque? Wait, does anybody know? Huh? Guys, what's the formula for torque? Yeah, R cross F. So some radius crossed with the force. Radius is measured in meters. Force is measured in newtons. If you multiply that, you get, yeah, newton meters. Yeah. Sometimes you also hear foot pounds. Right? If you guys ever hear foot pounds, that's sort of the American version of that. Okay. So newtons times meters. Now, here, guys, side note here. If you did multiply newtons and meters, could you say that looks kind of like joules, some number of joules of energy? Except, do you ever quantify torque in joules? Do you ever say, oh, torque is some number of joules? Do you ever say that? No, because that's a completely different concept. Even though at a glance, oh, wait, it's not the same unit, but it isn't. Okay, even though it looks like quantity. Okay. Right. What is capital L? Angular momentum. Aha, and that's well. Here, I'll show you guys that one. Right, so there's different ways. You go kilogram meter squared per second. There's also newtons times meters times seconds. You see that one too. Right? And then if you have a change in angular momentum, you can call it angular impulse. Right? impulse is like some kind of change in momentum, isn't it? Okay. Oh, and there is actually, guys, is this unit and this unit the same unit? These last two cells right here? Yeah, those are the same thing, right? If you quantify something or the change in something, of course it has to be the same thing. So you might see either or both of these on the AP exam in a few weeks, right? So you guys get so far. That's far. Okay. We got rotational analogs. So all right, time in seconds is still time in seconds. All right. Now, first the kinematic one. Well, here, I'll show you guys. Right. So instead of how far in meters, it's how far is something turn in radians. Right? How fast, acceleration, but different text, right? So here's in a linear sense, and here's in a turntable sense. Okay. Right. Then here's what's sort of analogous to mass in a linear sense. So in a linear sense, say if you kick a soccer ball, the more force you put on it, the more it's going to accelerate, the more mass, the less it accelerates. Okay? But in a rotational sense, what sort of takes the place of M? Yeah, rotational inertia. Aha. Which is the sum of m r squared. Okay? If you add a bunch of points, m r squared. Okay? Oh. Ooh, what's the rotational equivalent of Newton? Isn't that Newton's second law of motion right there? I think it goes on A. It should say net force equals ma. What's the rotational equivalent? Yeah. Okay. Yeah, you get torque equals I alpha, and of course, torque results from R cross F. I should say this. It's two slightly different things. It shows up on another poster coming up. Okay. Each individual torque is R cross F. That's where torque comes from. Okay? Like turning a wrench, opening a door, right? Some cross product. You need some kind of perpendicular component between the distance and the torque. Okay. And if you have a net torque, suppose you have like multiple torques acting on something, there could be some net torque, and that results in some angular acceleration. I think so. Okay. Then, how about what's the rotational equivalent of? Actually, how do you read this in a linear sense? What is this? What is P? Momentum. Yeah, which is mass times velocity. And what's the rotational equivalent? Aha. Yeah, there you go. Angular momentum. So L equals I times omega. Is that a vector? Is L a vector? Yeah. Right. What that means if you have something rotating clockwise versus counterclockwise, you would treat that as a positive versus a negative value. How about uh what's this formula say? Kinetic energy is 1/2 mass times the speed squared, 1/2 m squared. And if you have a ball that's rolling, you might have to consider some energy went into making it rotate. What's the formula for that? Aha. Okay. So, a lot of times I'll put a subscript R here for rotational kinetic energy. Okay. So the linear version of kinetic energy, sometimes you'll see the word translational. Translational kinetic energy. And then we'll call this one rotational kinetic energy. Okay. And if there's a ball rolling across the floor, it can have a little bit of both. Right. It's moving along, but it's also rolling at the same time. Right. So 1/2 I omega squared. Right. And is energy a vector or a scalar? It's a scalar. So if you have something rotating clockwise versus counterclockwise, do they both have a positive kinetic energy? Yep, they sure do. Right. Right. You guys get on all these? Here's another one you saw right before spring break. Is if you have a turntable rotating, or suppose you have a car that's driving around a big old circular racetrack or some version of that. Right. How far have you gone in meters compared to how far have you moved around the circle, say in, well, I would say degrees, but let's use radians for sure if you're multiplying by R. Right? If you use radians, then this equation can work. And so it can work for velocity and also acceleration. Right? Any questions on that turntable? Okay. All right. You guys remember, of course, these three kinematic formulas. But here's the rotation sense. Actually, let me see how you guys do. Here, guys, look up here. You guys see those three kinematic formulas? That refers to a turntable. How far does it turn? How fast? How much time has passed? We got angular acceleration if it's speeding up or slowing down its rotation. All right, pop quiz time. Walk around in your notes. See in your notes. You can write those three kinematic formulas for a turntable. Yeah, you need tape, paper. Everybody needs paper. Paper. Who else needs some paper? Oh yeah. All right. Alex got him. Hector got him. So we guys working on these. All right. Ray knows them. Yeah, Jack knows them. Alec knows them. All right. Rowan knows them. The three rotational kinematic formulas. Okay. So here's okay. So a bunch of you guys do remember these. Okay. So this is analogous to x equals v naught t plus half at squared. Right. Like if you go to the edge of a cliff and throw a ball straight down. Right. Now, guys, what if this starts from rest? A turntable starts from rest. Maybe you wind a string around it and pull it, and it starts speeding up. Which of these three terms can you get rid of? Yeah, this one right here. So that would just be 1/2 alpha t squared. What if there's no angular acceleration? For example, the Earth is rotating at a constant rate. Okay, how far does it turn? Right, which term can you get rid of? Yeah, this alpha would be 0, so this bit would go away. You got distance equals speed times time. Okay. How about okay? Here's all right. Final velocity equals initial velocity plus acceleration times time. Of course, for a turntable. Okay, and then you got all right. Final speed squared equals initial speed squared plus 2ax. Okay. All right. All right. Also, before spring break, I had you guys make the 3 kinematic graphs for a turntable slowing to a stop. Okay, so these are definitely in your notes from a couple weeks back. Okay. So I should say slows uniformly to a stop. What does omega versus t look like for slows uniformly to a stop? Wait, is it the middle one?
Oh, the middle. Oh,
Yeah.
downward linear.
Yeah, downward linear like this because it has some initial speed. It slows to a stop, goes to 0. Okay. And wouldn't that be a constant negative acceleration? Okay. So we got that. And then the tricky one is displacement versus time. Right. So how far does it turn as a function of time? What does this graph look like? Yeah, there you go. Upside down parabola, vertex at the top. Okay. So one of the things is if you break down to a few seconds, a few time intervals, right? First time interval goes a long way because it's going really fast. Next time interval, it doesn't go as far because it's slowed down. Last time interval, just a little bit because it's slowing to stop. Okay. Here's those rotational inertia sticks. Okay, so the formula for rotational inertia, now if you're looking at points or point maths, you just do mr squared. Okay, and then you can add them all up. Okay. So here, if I ignore the meter stick, or say the meter stick is kind of small or negligible mass compared to these two masses, I can just focus on these two masses. So I got this m times r squared plus this mr squared. You guys see that's where I get the 2 mr squared. Okay. And here I got, if I triple the distance, tripling the distance does what to the rotational inertia? 9 times because it's being r squared. So I got m times 3r being squared. That's like 9r squared here. I got another 9r squared here. Add it all up. That's 18r squared. Yeah, and then this compared to this. Yeah, it is 9 times, isn't it? It's 9 times. Okay. Now, if you did include also the meter stick, or if the meter stick was significant mass compared to those other masses, then maybe I'd have to break the meter stick down into like a billion points and say what's the mr squared here and here and here and here. Okay. And that turns into a calculus problem. That's been solved on. Here's the solutions for all these different shapes that can rotate. Now, notice these are all defined as rotating about some central axis. So this each moment of inertia that I typed in red only applies relative to that axis that it could be rotating about. Okay. So for a single point, of course, it's mr squared, right? And then, for a ring, that's really just a series of points that are equidistant. So that'd be the same thing. Okay. But all those other ones work out a little bit different. Notice it's always some coefficient of mr squared, though. You guys see that? Okay. Or in this case, with the rods, ml squared. Okay. Now, would AP expect you to memorize all these? No. Would they want you to maybe apply these and could give you a formula and want you to apply it? Yeah, actually, you're going to see that. I know you're going to see it because, this is definitely going to show up. So they might tell you, say like, here's a solid cylinder rolling across, or probably pretty close to this. They might tell you I equals 1/2 mr squared, and it'll tell you some kind of torque and ask you to solve for the angular acceleration. Okay.
been quite on its side and wrote on a friction surface, does it have a different rotational inertia?
Okay, so the thin corner on the edge. Okay. Here's the thin corner on the edge is like this. Okay. So as long as it's rotating just like that, it'd be 1/4 m r squared.
If it's like a turntable, what's the rotational inertia of the turntable? Does it have one?
Oh, okay. A turntable is actually the solid cylinder, basically. Like if I just turn this 90 degrees or make this like really flat, like how thick this is doesn't really matter. Okay. So there's your turntable. So the turntable is 1/2 m r squared. Okay. Yeah. And then this coin, if this coin was rotating like this, suppose it was like in deep space, just rotating like this, that would be back to this. Okay. And if it's rotating on, suppose it's rolling like this, or it's kind of hard to get it rolling like that. Okay. That's you start with this, but then you have to also include parallel axis theorem, which is actually the next one. Okay. All right. So you guys ready for next one? Okay. So what if something's rotating not about one of those defined axes from that table? Okay. Well, you can start with the value off the table, and then you add md squared, where d is the offset distance. So here I've got this basketball that's like orbiting around this axis that's parallel to its own central axis. Okay. So here's the axis on the table, and so if you have the basketball spinning on your finger, the associated inertia is like 2/3 m r squared. Okay. So if you give it a little flick to maybe try to spin on your finger, how much sort of resistance to motion do you feel? Oh, 2/3 m r squared. Okay. But if it's rolling across the floor, then you take that 2/3 m r squared and you say, well, this offset distance would be its own radius at this point. So you add another m r squared. Okay. How about the coin? Let's do the coin. If the coin's rolling like that, you guys see the coin rolling? Like that? Ooh, that's a pretty good roll. Okay. So you start with 1/2 m r squared, and then you add another m r squared. Hey guys, what is 1/2 m r squared plus m r squared? That'd be 3/2 m r squared. So say if I had actually here's a kind of the same thing. If I just start with this and come along and give this a push, while I'm giving it a push, I feel some resistance to change in motion, right, in a rotational sense, and that would be the 1/2 m r squared plus the fact that it's rolling would be another m r squared. That gives you 3/2 m r squared. Right, so you guys go with parallel axis there. For sure, this is going to show up on the exam. Here's how I know. AP has not included this on the AP exam in the past few years, but they included this new this year. So you will be asked about this. Okay, you'll be asked to apply this. I'm pretty sure we did an FRQ at some point where this showed up. Yeah, I know for sure. I remember now. This has shown up before. All right, let's do torque. All right, so here's your R cross F. Okay. And if there's a net torque, then that's going to result in an angular acceleration. So I times alpha. Okay. So when I say a cross product, you only multiply the parallel or perpendicular components. Perpendicular. Okay. So in fact, if you push straight perpendicular on this wrench, so here's the lever arm, here's the pushing force. If those are exactly perpendicular, you're maximizing your torque for however hard you can push. Okay? Because guys, what is sine of 90 degrees? 1, which is as big as that would maximize the sine value when sine of 90 degrees is 1. Okay. Guys, what if I have the wrench and I push exactly parallel to the handle? So I push this way. Is that ever going to turn that wrench? No, there would be 0 torque. And then in this case, theta would go to 0 degrees. What sine of 0 degrees? It would be 0, right? So that would indicate no torque. Yeah. All right. How about is it possible, guys? Is it possible that instead of this angle theta, they could give you this angle up here? Maybe I'll call it like beta. Yeah. If they do, guys, if they either give you this angle up here or this angle down here, which is the same thing, same beta. Right. How would you change this formula down here to solve playing off that angle? Yeah, this would change from sine to cosine, wouldn't it? Right. So be careful about that. This is sort of a textbook definition of torque. Right. It's the angle between the two vectors. Now, if you do the angle from the perpendicular, yeah, this would change from sine to cosine. Right. All right. You guys remember this big fancy lab? Actually, I think I guided you guys through this one. And I remember there was an AP video, I think I had you guys watch too. It was sort of a version of this. So what if I want to know if something's rotating, either a big pipe system or you have like a big wheel, like what's the rotational inertia? So we went through this whole process. Here, I'll walk you guys through the process, this lab that we did. Okay. I could hang different masses, or like different lab weights And so treat that sort of as an independent variable. Okay, measure all those. And then that would create like some tension in the string. Right? Oh, guys, which value is a tiny bit bigger? The weight down or the tension pulling up? Huh? Guys, is this going to overall accelerate down a little bit? Yeah, which means which force has to be bigger? Yeah, the weight's a little bit bigger than the tension. Although if it's a pretty slow acceleration, it's not too much of a difference. Right? When you have some tension in the string, and we have the radius of this pipe, which was I think about a centimeter, right, back a few months ago. Right? That results, guys, what is this R across this tension force? That creates a what? A torque, right? Which is going to cause this whole pipe system to not only rotate, but speed up rotating. That's called angular acceleration. Okay? And isn't it true? If you have more and more and more mass here, that would give it more and more and more rotational inertia. Okay? So suppose I start off with like these masses here, right? And let's think of what if I treated this as independent variable? I know we didn't quite do this, but just make believe. What if I replace those with these two big guys right here? And then it just massively increase the rotational inertia, right? So not m r squared. What would that do to the angular acceleration? Make it what, bigger or smaller? Smaller, yeah. So tau equals I alpha. Here, let's go back to that one. So I'm thinking sort of in terms of this framework. Right? If you increase that I, you'll decrease the alpha for some given torque. Okay?
So the torque's radius is the radius inside the pipe, but or of the pipe, but the I's radius is the radius of the two sinking on, right?
Okay, yeah. So you're right. There's different radial sizes going on. Okay. The reason the torque, I'm playing off the radius of the central pipe, is because this string tension is acting at that radius. It's just wound around the center of the pipe. So when I do torque equals R cross F, this R is, yeah, exactly this R right here. Okay. Right. Now the whole pipe system, yeah, if you're adding masses way out here, right, and suppose you're like sliding them around up here. Yeah, that's a different radial size, right? And that would play into the rotational inertia differently. Okay. All right. Ooh. All right. Let's do, well, yeah, I'll show this to you guys, but I should ask you guys this, is what are the conditions for equilibrium? I have 2D equilibrium, 3D equilibrium. Now, here, I'm kind of curious, guys, show of hands. Who's thinking they might maybe want to do engineering in college? Who wants to do engineering in college? All right. Yeah. Ooh, so that's almost half the class. Right. Oh, I know. See, I did civil engineering, and there's whole classes that are just based on this green box right here. Right? I mean, if you're going to build a big static structure, here's your conditions. Here's your starting conditions. Right? Some force goes to zero, then some torque goes to zero, and then you do this in each of the 3 dimensions. Okay. Now, for you guys, for this AP exam coming up in a few weeks, I mean, you're going to get this question, but they'll probably simplify it to just a 2D model, like a 2D plane, right? So you could say the forces in the X and Y direction go to zero, and then, well, I have the torque in the Z direction goes to zero, but AP just refers to clockwise or counterclockwise, right? So, okay, you guys do that. And that would only be one torque condition it would boil down to. All right. Speaking of which, that's the next few posters coming up. Okay, so you guys remember seesaw equilibrium? Okay, so here I can set up one right here. Let's say here's my pivot point. Here's my ruler, which is pretty light mass. What if I want to know? Let's figure out what's the mass of a quarter. You guys know what's the mass of a quarter? I don't know. Let's find out. So if this is balanced, I gotta get this balanced right here. Right. I can take this known mass. Now this is 50 grams. You guys see 50 grams? Okay. I can park this on one side. Right. You guys ever like go to the doctor, get your weight measured? They use one of these balance beam scenarios, right? Slide this quarter up. Okay, actually it's pretty big by comparison. All right. That's pretty close to balanced right there. Right there, right? Actually, this is pretty big, but whatever. Well, let's do it. Okay. So this radial arm from 15 to about 16.5 centimeters is that about 1.5 centimeters right there. Okay. And this quarter is over on the 1 centimeter mark, which is from 15. Guys, what's 15 minus 1? 14. Okay. So I have 1.5 centimeters here. I have 14 centimeters here. Okay. So I have a calculator. So off screen, I'm going to calculate what is the mass of the quarter? You guys also calculate it. Let's see if we all get the same thing. So again, I have 50 grams here. So 50 grams. This is a 1.5 centimeter radial arm. And then the quarter is 14 centimeters over on the other side from the pivot point. I'm just holding it balanced, but pretty well balanced. Okay. I have the mass of the quarter on my calculator screen. Okay. Who else has the mass of the quarter? What you got here? Ah, that's what I have too. A little over 5 grams. That's what I got, 5 grams. Okay. So all I did was I said torque equilibrium. I said the R cross F on the left side has to balance out with this R cross F on the right side. Okay. So something like that. So yeah, I'm getting about 5 point something grams. Let me Google the answer. We're gonna see. We're gonna find a moment of truth. What is the mass of a quarter in grams? Mass of quarter in grams. Mass of a quarter. 5.67 grams. Look at that. Physics once again. Oh yeah. Oh yeah. Look at that. How about? So you guys go with the seesaw? Okay. How about the kind of alternate version of this, the scaffold, where you're holding up with 2 supports, and maybe there's mostly one weight pulling down. Now, depending on how complicated you make this, you can either also include the weight of the beam, or sometimes they just say the beam has negligible weight. Okay. Let's do that. Let's do an example where the weight of the beam is pretty small, so I'm just going to ignore that. And we'll figure out if I tell you this weight, what could these 2 tensions be? Okay. You guys want to solve that? Let's do that. So make up something here. Okay. So I got a negligible mass, negligible weight beam. Let's say, how about this guy? Bam, 1 kilogram. You see 1 kilogram right here? In a park. This is a 1 kilogram lab mass. Let's park this at, how about the 70 centimeter mark? So I'll call this 70 centimeters. Okay, and let's say this is a meter stick. So if that's true, what distance would this be right here? Yeah, this would be 30 centimeters. Okay. And so I got a couple of spring scales on the end. Spring scale. Spring scale. You guys tell me, what are the force readings in those spring scales? I'll call it the force on the left side and the force reading on the right side. So force left and force right. What are those 2 force readings? Okay, go ahead and solve that. Who knows? Who knows those force readings?
Bro, you're always looking at like sports stuff on YouTube. I don't know where you're going.
How about now? Who knows the answer to that question? Who knows? Anybody know? Ah, Hector got it. Hector knows. He's getting 3 newtons right here and 7 newtons right here. Right? Do you guys see sort of a shortcut cut rule of thumb, which is the fact that this is 70% over to the right. This one is going to hold 70% of the weight. So, guys, how much does 1 kilogram weigh in newtons? 10 newtons, right? Right. So these 2 spring scales only have to pull up with also 10 newtons to balance out, so there would be 0 net force. Right, 10 newtons down, 10 newtons up collectively. Right? And it turns out that there's, 7 newtons on the right side and 3 on the left. Now, if you want to show, like, how do you show that? So your two conditions are, the sum of the forces goes to 0. That's what I just said. So 10 newtons down, 10 newtons collectively up. That's that one. Okay. And the sum of the torque goes to 0. And we're thinking sort of like clockwise, counterclockwise for AP. Right? Clockwise, counterclockwise. Okay. So these are your two conditions. Okay. Here's the full equations on these. But let's play off this one. So I need to pick some point as the pivot point. Now, guys, can I pick any point as the pivot point and the torque still sums to 0? Yeah, okay, I forgot. Let me write down my conditions. The sum of the forces go to 0 newtons, and the sum of the torque goes to 0 Newton meters. Okay, here's your two conditions. Okay. Oh, so let's say, all right. Now, here, I'll make an equation out of this first one. Okay. So the sum of the forces goes to 0. That means that force left plus force right up. So force left plus force right, I'll say minus this weight, and you know this weight is equal to, you guys told me 10 newtons. Okay, so mg equals 10 newtons. Okay. So minus the 10 newtons has to go to 0. Okay. So there's one of your conditions. Okay. But there's two unknowns. Guys, can you solve one equation with two unknowns? No. All right, so we need the other condition, which something to do with torque. All right, okay, so now back to where I was. Okay. Can I pick this point right here and the torque would go to 0? Yeah, in principle it would. Could I pick this point off the meter stick and the torque will still sum to 0? Yeah, right. But there's usually either a more intuitive point or like a mathematically convenient point. For example, is if you pick either one of these points, do you guys see that you'd be picking a point that's at the location of one of the unknown forces? Right? And you guys tell me, if I go open this door, suppose fire alarm rings, we gotta get out of here, hurry. I start push on this push on these door hinges. Is this door ever gonna open? No. So that would be 0 torque. If the unknown value goes to 0, gets rid of, sounds like it'd be easier to solve for the other one. Okay? I'm gonna pick this point right here as my pivot point. I'll label that pivot. Okay. And mathematically, that's a really nice choice. Okay? Because relative to this point, if this is my door hinge, then this weight is trying to cause what kind of torque? Clockwise or counterclockwise? Clockwise. So there's some torque from the weight. Okay. And then this spring steel on the right side, isn't this holding this back in check with that counterclockwise torque? Which is the exact same value, it's just the opposite direction. Because torque is a vector, isn't it? So clockwise and counterclockwise cancel out. And that's this condition right here. So I'm going to take this one and set up the other equation, which goes like this. 70 centimeters, so R cross F. You guys remember torque is R cross F. Okay. So at 70 centimeters, I have 10 newtons. So there's R cross F there. Of course, they're already perpendicular, so sine of 90 degrees is 1. Okay. Minus, and then at the full 100 centimeters, I'll have my unknown force on the right side. And this all zeroes out, 0 Newton meters. Okay? All right, that all right? All right, you guys write that in your notes? Okay. Then, now we can solve right away for what is this force on the right side. So I can add over 700 Newton centimeters, divide by 100 centimeters. And guys, what's 700 divided by 100? 7. So the force on the right side, the only number to plug in there to make that work is 7 newtons. Okay. So, yeah, it's exactly what I was saying before. Okay. So this has to be 7 newtons. Okay. You guys got it? All right. Then we still got to get the force on the left side. Haven't done that yet. Well, that's this condition back here. So I set up the equation for that one already. Okay. So if you put 7 newtons right here, then what's the answer to the force on the left side? 3. Because 3 and 7 minus 10 would zero out. Okay. So then I can say, bring in this right here, boink and boink. That gives you a force on the left side is the other 3 newtons to zero out the forces. Okay. Or maybe you could have picked this point on the right side as the pivot point and solved it a completely different way. Of course, you would end up with the same answer. Okay. All right, you guys get there? You guys can solve the scaffold? Scaffold. Ooh, a ladder resting against a frictionless wall. This is a classic physics question. I wouldn't be surprised at all if you guys got this question. So here's what we do with this one. Let's just draw this one, and I'll have you guys draw the free body diagram for this situation. So I have a floor and a wall. You guys see a floor and a wall. Catch this in. Okay. And let's have a ladder resting at some angle. So here's your ladder. So ladder rests against a frictionless wall. Okay. Now, even though there's no friction from the wall, does there have to be friction somewhere in the system? Yeah, because if there was no friction against the floor, then what would this ladder have to do? Yeah, it would have to slide like that. It definitely couldn't be at rest, right? It would have some kind of torque at some angular acceleration. It should be falling faster, faster, faster. Right? So we're just going to say it's at rest, so equilibrium. But there's no friction from the wall. There might be a different force from the wall, but not friction. Right, go ahead and draw the free body diagram. FBD. Actually, you know what? AP probably won't call it that. They'll probably call it a force diagram. Let me scratch that out. I'm going to write a different term. Force diagram. And the reason they're going to call it a force diagram instead is because different forces act at different locations on the ladder. Free body diagram, you usually consider everything from the center of mass, but that's not true for the ladder because there's different forces at different locations. So they'll probably call it a force diagram. Okay, you guys go ahead and draw that. All right. All right, Alex got it. Hector got it. Alec got it. Jack got it. On this. I think I gave you guys another minute. I think some of you guys are on your way to getting it. Okay. So, guys, what's one force on this ladder? Yeah, it's weight. Now, even though its weight is distributed over probably like every single rung of the ladder, is it okay mathematically if I treat its weight acting at the center of mass, like right there? Okay. Yeah, that's perfectly fine mathematically. Okay, nothing wrong with that. What other force acting on this ladder? Okay. I heard normal force maybe from the floor. Right now, guys, the normal force from the floor, should I make it that big right there, or bigger or smaller? Has to be bigger. How do you know it has to be bigger? Here's your conditions right here. The sum of the forces horizontally go to 0 newtons. The sum of the forces vertically go to 0 newtons. And there's only two vertical forces on this whole thing. And it's the weight down and the normal force from the floor up. Normal force from the floor. Okay. And do you guys see how those two are zeroing out? So that's that condition right there. Okay. You said what other force? Oh, friction from the floor. Yeah. So down here at the base, I'll do F sub FR from the floor. Okay. And what else? Other force? Yeah, normal from the wall. Okay, so here's Fn from the wall. Okay. And I know that these two have to zero out. Okay. Actually, I don't think my picture is exactly to scale. And here's how I know that. Because if I make a triangle with like these two forces, or if I connect these tip to tail and I make a triangle, I know that triangle should actually be similar to the actual geometric triangle with the ladder against the wall there. So I should make these a little bit bigger. Okay. Because they would have to follow the same angles. All right. So so here's your force conditions. There's also, of course, a torque condition. The sum of the torque goes to 0 Newton meters. So if you consider this point, hey guys, could this point down here with the floor be a really good choice as a pivot point? Yeah. Oh yeah. What's that? Oh, it's a frictionless wall. Yeah.
Oh.
Yeah. Okay. But you're right. You're right. Probably a more realistic scenario is true. Guys, if the ladder's trying to slide down, probably realistically there actually would be friction with the wall, but that would be a much more complex puzzle. Okay, so they usually just simplify it to this one. Okay. Yeah. So guys, if I pick this point down here as the pivot point, did you guys see kind of like the last question with the scaffold? You guys see that these two forces would cause 0 torque about that point? And so in a torque equation, they would immediately zero out. Okay. So I could get this radial arm crossed with this weight, canceling out with this radial arm crossed with this normal force in the wall. So here's my two radial arms relative to that pivot point. Okay, you guys see it too? Okay, I want to see if you guys can figure that out. What is the length of this radial arm right here? You guys see this? I'm going to call this R for the radial arm with the weight. Like the weight of the ladder is trying to cause some torque relative to this pivot point. You guys see it? Okay. Now, if I tell you the length of the ladder is L, so length of the ladder is L, and what if I give you this angle down here from the floor? I'll call that theta. Okay. Who can tell me what is R, this radial arm right here, in terms of L and theta? Ah, yeah. So L over 2, and then cosine theta. There you go. That'd be the radial arm for that would play into the equation. Torque equals this radial arm crossed with this weight would create some kind of clockwise torque. All right. So you guys good with the ladder? All right, so good with the ladder. Okay, and then there's the full version of that. Here, I'll show you guys this full one, but guys, this is a really critical poster right here. You're going to get this question. You're going to get this question. So if you tie a string around a turntable and pull it, it's going to cause it to not only rotate, but it shouldn't be speeding up spinning because there's a net torque on it. Right. Guys, what would the torque be equal to in terms of the variables on the page? Torque is equal to what times what? Yeah, R cross F. So this R crossed with this F. So if you have a constant tension in the string, the tension would be the force. Right, crossed with this R, we provide a torque. Actually, how AP usually phrases this particular question is they usually just give you the torque. They say, okay, wind a string around, and they just tell you, just jump straight to what the torque is. Okay? But if they don't, R cross F, that will get you there. Okay? Right. And that will result in some I times alpha, as long as there's no frictional torque to subtract from it. Right? So net torque results in I times alpha. Right? If you know the rotational inertia of the disk, which you could get one of two ways. Either AP could give it to you directly, which they probably would, or guys, if AP does not give you I directly, how could you possibly calculate the rotational inertia for that? Yeah. Isn't it actually this one right here? Just turn vertical, 1/2 mr squared. Right. So any kind of disk rotating about its center is always 1/2 mr squared. Okay? Because they're rotating about different axes. Yeah, this coin is spinning about the central axis. And this, okay, so yeah, so question is why are these two different? Okay. So they'd be the same as long as the coin is rolling. Right? If this coin rolling actually is this one. But if it's spinning about this axis like this, then it turns back into this. Okay. Yeah. Whoops. Okay, here we are. Okay. So you could do 1/2 mr squared, and you could calculate the rotational inertia of the disk. Okay. Then, if you know the rotational inertia of the disk, 1/2 mr squared, and you know the torque to be R cross F, could you calculate that alpha right there? The angular acceleration of the disk? Spinning up, spinning. Okay. Also, while the disk is spinning, it's going to have some of this angular momentum, so I times omega. And if it's rotating faster, here, guys, if it's rotating faster, would this value be constant or would it be increasing? Increasing. Right, okay, here's your RF equals I alpha. I think I got one more for you guys today. This is a story that you could apply, or a pair of graphs that you could apply to that story. So if you apply a constant torque, so that'd be a constant tension string and a constant radial size, that could give you this graph. And it would be speeding up spinning, so the angular momentum would, in fact, be increasing, just like you guys said. If you know one of these graphs, you can know the other. One time in the past, I've seen AP increase the torque. So this graph looks like this. Guys, if this graph is increasing at a constant rate, what does this graph on the right side look like? Aha, it'd be a parabola, wouldn't it? I've seen AP do that before. Okay? But usually it's some version of this. All right, so you guys good? Guys good? All right, well, we got 5 seconds to the bell, so let's wrap that up right there.